It's being recorded.
Okay, so today we'll talk about the model structure on simplicial categories. So first, I have to talk why do we care about this, and it's because. So okay, I'll start. So idea, we know that S set of the category of simplicial sets. Here we have a subcategory, a full subcategory, Q S set, Q-cat of quasi-categories, which are a model for infinity categories. But this is not the only model we have for infinite categories. Another model is that of simplicial categories, which we take to mean categories enriched over simplicial sets. So is a category C, whose home sets are objects of our simplicial sets. But not only that, we say that an infinite category in the model of simplicial categories is a category enriched over quasi-categories. So we require that here we have this. The problem is we have two models. But fortunately, we can see that there's a strong relation between them, in the sense that we have a model structure on S set, the JL model structure. Here we have in catch S set, which are categories enriched over simplicial sets. We have the Bergner model structure and a functor called the homotopy coherent nerve that takes a enriched category over simplicial sets, returns a simplicial set, such that this admits a left joint, here S, such that this is a Q equivalence with these model structures. Here, the cofibrant objects are infinite categories, that is, quasi-categories, and in the Bergner model structure, the fibrant cofibrant objects are the enriched categories over Q-cat, that is, that the home sets are infinite categories. So here, the weak equivalences in the JL model structure are the equivalences of infinite categories, and here the same thing. So at least we have some form of comparison between these two models. So, okay, with that being said, we'll start by, okay, so today I'll only define the model structure on cat S set and won't show this equivalence, but yeah, that's it. Okay, so as I said, a simplicial category. Here we take to mean a category reached over simplicial sets. So before we can define the model structure, we have to talk about some preliminary notions that of homotopy equivalences in a simplicial category and a homotopy category of a simplicial category. So I'll start with the latter. Given a map of simplicial categories, that is a map of objects, and for each xy of C, we have a morphism of simplicial sets. Okay, this is a enriched functor, a set enriched functor. So we will define a functor p pi 0 of f that goes to pi 0 of C to pi 0 of D, which this is the homotopy category of C. So first we have to define this object here. So we take pi0 of C to be the category whose objects will be the same objects as of C. So this equals C. And morphisms. So here we have a complex of morphisms. So we take the morphisms pi0 from x to c, from x to y, to be the connected component of zero simplices of this S set. So this equals pi0, which by definition equals the set of zero simplices quotiented by equivalence relation given by the edges of the complex. With this defined, we have that pi0 f here just takes, we know that if for a morphism of simplicial sets, this translates to a morphism in the connected components by the naturality of alpha. So we have an action, we have a functor pi0f that is whose action in objects is the same as in C, and the action in morphisms is that of the morphism quotiented here and here by the equivalence relation. So we have this pi0 functor, and this is the homotopy category. That is to say, we have a functor pi0 that goes to catch as set to catch. We see this plays a fundamental role in defining the model structure. Namely, this will kind of give us a way to take the canonical model structure here. That is the only model structure in CAT that localizes equivalence of categories. So, okay. Another construction we shall need to define the model structure is that of homotopy equivalences. Now, they will be internal to a simplicial category. So, a morphism x to y, when x and y are objects of a simplicial category, is a zero simplices here. So we say that f is a homotopy equivalence here, is a zero simplice. The morphisms are taken to be zero simplices. And for instance, the higher simplices are higher morphisms. So that's why simplicial categories are a model for infinity categories. So f is a homotopy equivalence if f is a isomorphism in pi0 of C. So that is to say that we have f, a zero simplice here. So f is taken to a class of equivalence of f that goes to from the same objects, because the objects of pi0 C are the same that of C. And yeah, so this is the definition of homotopy equivalence. So, okay. With these definitions in hand, we can define the model structure. So, model structure is by definition. Oh, last thing I forgot to mention. I'll not prove this, but theorem CAT as set, the category of simplicial categories, is complete and co-complete. This is necessary for for we to have a model structure. So a model category. Model categories are by definition complete and incomplete. Does it make sense to ask for a model structure here? Okay. So we must define what are fibrations, cofibrations, and weak equivalences. So I will start by defining what are weak equivalences. And to do that, I'll use the model structure, the killing model structure on simplicial sets. We have, I talked about the Joyal model structure, and the killer model structure here. The fibrant objects are complexes, so this gives us a clue how we'll make the cofibrant objects of simplicial categories be the complex enriched categories. Okay. Oh, sorry. I now realize here I said that cat as such the fibrant objects will be categories enriched over infinite categories. That is false. Will be the categories enriched over infinity groupoids, complexes. There are the notion of infinity groupoids with using S set as a model for infinite categories. So, okay. So, okay. Just to make it clear, because what I said before was wrong. Okay. So I will not define the killing model structure here because I think it is quite well known. So I know that Daniel knows. Okay. First I'll define fibrations or weak equivalences. Okay. So fixomorphism here between simplicial categories. We'll say that F is a weak equivalence of simplicial categories if these two conditions are satisfied. We saw that this, by definition, for every xy objects of C, we'll have that F here is a morphism of simplicial sets. Here. So we'll say that F is a weak equivalence if all these maps are killing weak equivalences of simplicial sets in the sense of killing. So this is a model for topological spaces. You can think of that by definition. This weak equivalence here is to say that the geometrical realization of this morphism is a map of topological spaces that induces a isomorphism in all homotopy groups. So there's the definition. But not only that, we require that this is to say that F is locally a weak equivalence, in the sense that in all home sets it is a weak equivalence. But not only that, we require that pi 0 F that goes to pi 0 of C to pi 0 D is essentially surjective. So I want to talk about this for a while. So first observation here. Condition 1 here. So condition 2 plus condition 1 implies that pi 0 of F is a equivalence of categories. To see this, we note that if this is a weak equivalence, then pi 0 the induced morphism here is a bijection. Okay, so the condition saying that this is essentially surjective is saying that we have a fully faithful functor here, because this map is a bijection for all x and y, and is essentially surjective. So it is an equivalence of categories. And lastly, about this definition, I wanted to talk about this condition too, because this condition is the same as saying something like f is homotopically essentially surjective. So this makes sense because we are not thinking strictly. We are thinking of in the with weak equivalences in mind. So in a category, for example, in the category of categories, we say that a functor is fully faithful if for a functor here, an honest functor, not an enriched functor, here we're in cut. We have that this is a bijection. What are bijections? These are simply isomorphisms in set. But we are thinking homotopically. So to ask for this to be an isomorphism of simplicial sets, the same way we ask this to be isomorphisms of sets, would be too strong because we want to think about the weak equivalence. So we ask it to be homotopically fully faithful. That is to replace an isomorphism with a weak equivalence. The same thing for essentially surjective. We do not require it to be essentially surjective because this would mean that we have to have strict isomorphisms, but we want some sort of weak equivalence. So this is why we replace for these weaker conditions. Okay, this is just to give an idea of why we ask this. So, okay, this is the definition of weak equivalences. Now we move on to the definition of fibrations. So we have something similar. Here, I'll talk about after I define this. Okay. So F2. This is again we require a fibration to satisfy two properties, F1 and F2. So first of all, F must be a local fibration. That is to say that for all home sets, home simplicial sets, another name for this is the function complex. I'm just using home sets because it's shorter to say. So function complex. Yeah. F of x, f of y. Is a confibration. So I'll write this. So it's a fibration in the Killing model structure in simplicial sets. So those are the maps that have the relifting property against all hard inclusions. So we have an inclusion here. This morphism lift. So this is the definition of a confibration. Okay. F2, we have something similar. And after that, I will make a remark because this is very similar what is happening. So, okay. We require that F is a homotopical isofibration. That is to say that if we have a weak equivalence, and homotopic equivalence in the sense of this definition here, that the induced morphism in the homotopy category is an isomorphism. So of this form here. So this is in D. Remember that this is to say that E is a zero simplest. Then there exists a homotopy equivalence D, also a homotopy equivalence. Okay, that goes from F to Y, such that F of D equals Z. So this implies that F of Y equals B. So this is equivalent to say this: pi 0 of F, that goes to from pi 0 of C to pi 0 of D, is an isofibration, where an isofibration is a fibration in the canonical model structure on the category of categories that localizes weak equivalences. So, okay, so now I'll make a remark to see why this is similar. Okay, so in these two definitions, we have two items. Both items 1 say that this is locally something that we want it to be in the category in which we are enriching our objects, so our home sets. So here we want it to be a weak equivalent. So we say that it is locally a weak equivalence in the model structure of the category in which we are enriching our categories. Here the same thing. We require to be locally a fibration, a can fibration, and here a can weak equivalence or Killen weak equivalence. The second condition says something similar, but in another model structure. Here we are in Cat, the model structure. This is saying that pi 0 of F is a weak equivalence in Cat. Okay, and here we are saying that because to note this, I said that condition 1 plus 2 implies that here is an equivalence of category. And by definition, the weak equivalences in Cat are the equivalents of categories. So here we have the same thing. We have a condition that mentions locally the model structure of the category in which we are enriching, in this case as set. So, and here we have this the same thing as before, but now in the model structure in Cat. We said here that this is an equivalence of category, so it's a weak equivalence in Cat. Here we said that this is an isofibration, because this is equivalent to this homotopy lifting property here. Not lifting, you know, pull back, I guess. So, yeah, this here is an isofibration. That is to say that pi 0 is a fibration in the model structure of Cat. And I will not talk much more about this, but this gives us a hint that we can try to replicate this in general for if we have a V monoidal model category. We may try to give the category of V enriched categories a model structure. Following this, we will have morphisms between S sets, and we may replicate this. And this functor here, pi 0, we may define this in general, but it's not so simple because S sets are really nice, so it's really easy to define this. It's not that hard to define it here, but I will not talk much more about this. Okay, so this was the remark. Now we have defined weak equivalences, we have defined vibrations. The only thing remaining to define is the cofibrations. But as in any model structure, having defined the first two, it is necessary for this to in fact be a model structure that the cofibrations. So here it is but we have to have that this is the morphisms that have the right lifting property, left lifting property against the acyclic vibrations or trivial vibrations. That is, say, the maps that are vibrations and that are the equivalences. So, okay, here we have a model structure. And by a result of Bergner, this is in fact a model structure. Okay, so I'll talk. Not only that, this is not just a model category. So theorem here, cat as set with this collection of morphisms is a model structure. Not only that, this category is cofibrantly generated. So I will not give a complete proof of this today, but I will talk about what are the generating cofibrations and some of the idea of the proof. And after that, I'll talk about the fibrant cofibrant objects and see that they are in fact the category reaches over complexes. So as we said, that this category is cofibrantly generated. So the procedure of the proof is to define the generating cofibrations and generating acyclic cofibrations and prove one theorem like the recognition theorem, something like that. We will enunciate this theorem so that it's clear why this works. Okay, now I'll define the generating cofibrations, and as one might guess, we'll again base our generating cofibrations in the generating cofibrations on simplicial sets with the Killing model structure, which is also a cofibrantly generated model category by the Hard inclusions and whatnot. So, okay. Before I define this, we need to define a functor U that goes from S set to cat S set, because our generating cofibrations will be the image of some morphisms by this functor, which will take in simplicial set X to a category C, such that C has exactly two objects, and we have that C of X and Y equals X, C of XX equals C of YY, which equals the terminal object in a set, the zero standard simplex. So, okay, the action in morphisms is clear, right? We send the objects to object and send the natural transformation between simplicial sets to the natural transformation between simplicial sets, because we just require that the action in objects is right. So, with this in hand, we'll define the generating cofibrations. So, we'll have two collections. Here, I'll change the color because okay. So we have I1 and I2, two collections here. I will be to denote the collection of generating cofibrations. So this will be U of the boundary inclusions. So here, and this will require that this here, where this is the empty simplicial category, here is a generating cofibration, where this is the terminal simplicial category. So we have the I equals A1, I1 union with I2. So, okay, as I said, here, these are the generating cofibrations in simplicial sets. So this definition is quite natural, actually, because I'm not sure much of this, but this will give us a lift in every home set in the simplicial category. So to have a lift will be simply to choose the action in object, and then use that locally we will have fibrations and cofibrations, and the lifting property will follow from there. So now we have to define the generating acyclic cofibrations. So again, we'll have two collections. So the first one, as before, will be the image by U of the generating acyclic cofibrations of the killing mother structure. So we'll have here hard inclusions, and here it's a bit more enigmatic. We'll have that are the maps of the terminal category to the category, a simplicial category H, that I will not define here completely, but just because I'll not prove the model structure, I don't think it would be necessary because this is rather technical. But I'll say that H, all home sets of H are contractible, or that is to say that this morphism here is a weak equivalence, and that they are all not the empty category. So I actually discussed this with you, Daniel, that I don't know if we define this should be contractible. So I don't know if this condition already disclassifies this, but I'll mention this explicitly. That is to say, more or less, that H is a connected category, a connected groupoid, actually. But more or less, because here, if you have these are equivalents, okay, not important, actually. But, okay. So we have, these are the generating cofibrations, and we have a theorem that states the following. Just to give a hint, let's see. Here it's just a category, be a complete and co-complete category with two distinguished classes of morphism, W and Fib, here in the morphisms of C, such that W satisfies the 2 out of 3 rule. The 2 out of 3 rule, and is closed under retracts. So this is, we want that W be the weak equivalence. So in a model category, the class of weak equivalences is closed under retract. So this is not a problem to require this, because if this were not true, there would be no hope that this is a model structure. Okay. And suppose that there are I and J two collections. Here, this will be the generating cyclical vibrations, such that there are 4 conditions. I and J. How can I say this? They so admit. Okay, so admit small object arguments. I will talk about this means. 2. We have that vibrations. Oh, remembering that this is a distinguished class here, equals right lifting property of of J. 3. A cyclic vibrations equals the right lifting property of I, and that cofibrations so sorry, here in this we define the further this collection, that is LLP here, LLP. So, and that cofibrations equals LLP of then C Phi cof W is a cofibrantly generated model category. In which, of course, the generating cofibrations are I and J. So the proof of this model structure is simply to show that this collection satisfies these 4 conditions. So here, okay. Okay, there are 10 minutes. Okay, so as I said, here are the generating cofibrations, and I just have to say what this first condition means. So we say that a collection I of morphisms admits a small object argument if every morphism in C factor as a cell complex in I here, followed by a morphisms that have the right lifting property against I. So we need this because we must have factorization systems by definition of a model category. Not only that, this is fundamental in the proof, because the proof works by factoring things as such and using the retract argument. So okay, so idea of the proof. So I already gave some idea here. This is the theorem that we. So actually, I will skip this because I don't know if it is that important now. So I think this is much more interesting, and it's actually quite easy to see. Assuming that that is the model structure, what are the fiber and cofibrant objects? So, oh yeah, just one last remark here. The category S set, cat S set, sorry, with the model structure defined above is right proper. This is actually a quite nice property for a model category to have. So this is also in the original article of Bergner, where she shows this is a model structure. So yeah, this is good. Okay, so now we talk about the fiber and cofibrant objects. First, we show that as in S set, all objects are cofibrant. To see this, we must show that this morph take any category, fix a category here. So we have to show that this morphism here is a cofibration. So this is equivalent, the same by definition. To see that if we have here x, so x, no, e, just as in topological spaces. Here we have a cyclic cofibration. Here we have C, sorry. Okay, no, here, yeah. Here we have our map. I'll call it, here I'll call it P, and here I call it F. So we have to show that there is a lift here, because to complete the diagram is just the empty category here, but since this wall commute, we have to show this lift. Okay, this is actually quite simple to show. First, we have to define this lift. We have first to define the action of this lift, I'll call F tilde, in objects of C. But here we have that P goes from E to B. It's an acyclic vibration, so here. This is to say that this implies actually, no, that is not equivalent, that pi 0 of F is essentially surjective and an isofibration. It's quite easy to see that this implies that pi 0 of F is surjective on objects. Okay? So to see this, isofibration lift isomorphism. So since it is essentially surjective, we have that for every B in B, we have a morphism here, B. That is an isomorphism. Here, all in pi 0. Okay, sorry. This is pi 0 of B. So we must have an object y such that f of y equals b. Thus, here, pi 0 is surjective on objects. Not essentially surjective, but honestly surjective. So define f tilde of x, any object in C, where should be any object A of E such that P of A equals f of x. As we said, this is actually surjective in objects. The action of pi 0 of f in objects is the same of the action of f in objects. So f is surjective in objects. Thus, this always exists, so we may choose. Now, okay, so we use the conditions 2, right? We use W2 plus F2. This mentions the model structure on cat. Now we must use the the model structure in S set, the QA model structure. So why I say this? Okay, so we have now a choice of objects here. So we have a diagram like this that commutes. For every xy, we have b of f of x. No, sorry, I will need a bit more space. We have, for every two objects, we have a morphism like this. Okay, so we define the action of the f tilde in objects. So we must define its action in objects. So here, in objects, no, sorry, in morphisms. Okay, b, f of x, f of y. Here we have e, f tilde of x, f tilde of y. Okay, this is, by definition, this commutes here. Here we have, by definition, p was an acyclic vibration. So it is locally an acyclic vibration in a set. Okay? So here we show that, okay, but here is equal vibration, right? Because, oh, I made a mistake. Sorry. Okay. So, oh. Okay, here. Well, what happened here? I'm confused about something. Oh, the lifts. What is happening? So, no. Here we have a morphism like this. Sorry. Okay. Duh. So these lifts. Okay. Every time. This is equal vibration. Because every object in C, every object in S set is cofibrant. And this is by definition an object. Sorry, that was the confusion. So we have a lift here. Locally, we have a lift. And so we have an action morphisms. Thus, we conclude that this is equal vibration. Sorry for the confusion. You see what forgetting to add the whole diagram, because okay, now the proof that every object is vibrant is actually much easier. Not that this demonstration was hard, it's just that I got confused at the end. So vibrant objects. So an object is vibrant if this morphism here, sorry, okay. This is C. No. Okay. With, okay, so C is vibrant if this morphism here is a vibration. Okay. Thus, by definition, first note that F2 is satisfied immediately. Okay. Because here we have a single object and a single, and the morphism complex is just a bunch of points. So we always have a lift. here. Okay, because note that by 0 of f will be something like to the point category, So this is always a isofibration. So okay, condition F2 is trivial. Condition F1, we have by requirement that C, X, Y, here a fibration. We require that it must be locally a fibration. To the point here must be a fibration. But this is saying that Cx of y is fibrant for all xy. But the fibrant objects in as set are exactly the Kahn complexes, the infinity groupoids. So the fibrant cofibrant, okay, so conclusion here. Conclusion. The fibrant cofibrant objects of Cat as set with the Bergner model structure are the Kahn complex enriched categories. Okay, so this is actually quite nice, and I'll talk. So forget this. I'll not talk about this today. I'll just make a last comment actually, on this fact here. So, a naive intuition, when I say infinity category, I actually mean infinity 1 category. Infinity 1 category. So, because this is what we need to do homotopy theory. So that is to say that we have morphisms between morphisms, higher morphisms for every n, but for n plus or equal to greater than 2 or equal, we require the n cells to be invertible. So if we take a morphism Fg and look at the home sets between F and G, that is to say that if we have here, this is all naive, okay? I'm not referring to anything rigorous and whatnot. So if we have an infinity category C and then 2 objects, we are saying that here is a category, okay? Because we want to have morphisms between morphisms, but not only that, we want to have morphisms between morphisms. But here, the morphisms are 2 cells, 3 cells, 4 cells, and so on. But I'm saying that we actually are working in an infinity 1 category. So for cells with n greater than 2, this is actually isomorphism. These are actually isomorphisms. So we are saying that is a category where every morphism is an isomorphism, but not all morphisms, but all higher morphisms, because we not stop at one. They say that this is naively a infinity groupoid. So we are thinking here as a infinity one category, as a category enriched over infinity groupoids. Okay, so what is an infinity groupoid? That's another problem, but we know that complexes are a good model. These are actually spaces in the sense of top. This is quite nice also. Some people take infinite categories to be categories enriched over topological spaces. So here are good models for infinity groupoids. So what is it saying? That the fibrant cofibrant objects in cat as such are categories enriched over infinity groupoids. So, yay, okay, we have something that we wanted to be true, and it is true. So this model structure is what we wanted it to do. So, okay, quite nice. And as I said before, here okay, but this actually has this model structure relates quite nicely with the Joyal model structure, which is the model structure for infinity categories. So, okay, so that's it. Okay, so I'll stop the recording, okay, Daniel?